Hi everyone, this is Elisa Baum. I'm GridGain Systems Director of Product Marketing. We'll begin in a moment, but first I need to conduct a little bit of housekeeping. Could you please raise your hand using the hand icon located in the GoToWebinar control panel to let me know if you can hear me? Let's see, hands, great, thank you. Next, during this webinar, you'll be on mute, but should you have any questions today for Valentin, please enter them in the questions field within the control panel. At the end of the webinar, we'll take as much time as we have left to answer as many questions as possible, and those that aren't addressed will be sent off to Valentin for him to look at, and also we'll probably do a follow-up blog post on GridGain to address many of the questions. In addition, a recording of this webinar and a link to the slides will be made available to everyone within 48 hours. So with that said, I'd like to thank you for attending today's webinar, Building Consistent and Highly Available Distributed Systems with Apache Ignite and GridGain. It's being presented by GridGain Systems lead architect, Valentin Kulichenko. And with that said, I will turn the floor over to Val. Go ahead, Val.
Thanks, Alisa, and hello, everyone. My name is Valentin. I'm one of the committers of Apache Ignite project and also PMC member of Apache Ignite project. And I also work at GridGain as a lead architect and senior support engineer. And I spend most of my time working with our customers and Ignite users, helping to solve their use cases and different kind of problems or issues they have when working with Apache Ignite and GridGain projects. And today I want to share some of this experience with you. And in particular, I will talk about, I will give like particular guidelines on how to build both consistent and highly available distributed systems on top of Apache Ignite and GridGain. So let's start. This is the agenda of today's webinar. I will start with a quick overview of Ignite and GridGain projects for those who are not familiar with them yet. I will cover like basic definition of the projects and also some major key components that we have there. Then I will talk about how Ignite stands in the CAP theorem. And then I will move to the actual topic of the talk, and we'll talk about different features and components we have in Ignite and GridGain that allow to build more available systems. I will talk about cache backups, about persistence, data center replication, and data snapshots. And at the end, we will have a Q&A session where I will answer any questions that you have for me. All right, so what is Ignite? Ignite is essentially a memory-centric data platform, which basically means that we store data both in memory and on disk. This provides both good performance of in-memory and durability of disk. The system is strongly consistent and highly available at the same time. I will cover this in much more detail throughout the rest of the talk. And Ignite also provides multiple APIs to interact with the data, to talk to your data. This includes full NC99 compliant SQL support, key value API, ACID transactions, compute processing APIs, and many others like machine learning, streaming, and so on. Okay, so let's talk about some of the key components that are available in Ignite. So first of all, it's a key value data grid. That's a component that we have for a long time. Ignite has it since it was born, actually, and it's essentially in memory key value store, a distributed key value store, which can be scaled out across multiple servers. It's fully ACID compliant, supports transactions, including distributed transactions. It also supports collocated processing, and it can be integrated with different types of persistence. It can be both native Ignite persistence, which I will also talk about in more detail later, and pluggable third-party persistence as well, like RDBMS or any NoSQL database, HDFS, and what's not. Key value data grid is usually used for database caching or web session clustering or similar use cases. The second major component is a distributed SQL database. This is a fairly new feature. It was released in the latest release 2.1. And basically what this means is that you can interact with your data using exclusively SQL API. You can use native Ignite API, which is available in Java, .NET, and C++, as well as JDBC and ODBC drivers. Support includes not only querying the data, not only select statements, but also updating the data. We have full DML support, including update, delete, and sort statements. And you can even create your data schema using SQL. We have DDL support, which allows to create tables and create caches along with these tables. Change the configuration of these tables, create and destroy indices, and so on and so forth. And of course, it's also fully consistent, ACID compliant, distributed, and scalable. Okay, so now I want to spend some time talking about how Ignite stands in the CAP theorem. It's actually a very frequent question. I hear it a lot from our users and our customers, and I want to give my view on that. So first of all, CAP theorem is basically a theorem that tells us that any distributed system can have three characteristics: its consistency, availability, and network partition tolerance. And it also tells us that it's not possible to build a system that will have all of them at the same time. Basically, there is no system that is consistent, available, and partition tolerant at the same time. And the most common interpretation of that is basically that there is no way you don't have network partitions. Any distributed system will suffer from network partitioning, or at least it will be possible that it will suffer from network partitioning at some point of time. So partition tolerance is a must for any distributed system. So we cannot give up partition tolerance. And this basically leaves us with a choice between consistency and availability. And this actually makes sense if you think about it. In case of network partitioning, if there is some data that is lost, that is not available to the clients that are connected to the cluster, the cluster has two choices. It can either let client know that the data is inconsistent now and give an error, which will basically make the system unavailable, or it can make sure the system is 100% of the time available, but in this case, it will be possible that the client receives inconsistent result. And Ignite is strongly CP system. So Ignite chooses consistency over availability. It basically means that you will never get inconsistent result with Ignite. Ignite will prefer to give you an exception instead of giving you inconsistent data. But actually, I would also argue that Ignite and GridGain and any system built on top of Ignite and GridGain can still be highly available. What this means is that it will not be available 100% of the time, but most likely it will be available like 99.999% of the time. And there are different ways and different features available in Ignite and GridGain that allow you to increase availability and to make your system more available. And that's what I'm going to talk about in the rest of the webinar. Okay, so let's start with the cache backups. So having a cache backup basically means that you have more than one copy of any value in the grid, in the cluster. And there are two cache modes which behave in a bit different way, partitioned and replicated. Partition cache means that you basically just configure the number of backups you want to have. For example, it can be 1 backup or 2 backups or more. And if you have 1 backup, for example, you will have 2 copies of the data for any entry in the cache. For example, if you take a look at the picture on the left, we have 4 nodes here, 4 server nodes, JVM 1, 2, 3, and 4. And for example, we have entry A, which is stored on JVM 1, which basically means that JVM 1 is a primary node for this entry A. But this entry A is also available on JVM 2 as a backup. And what it provides is that whenever we lose a node, we don't actually lose any data. So for example, we lose JVM 1, we still have the entry on JVM 2. In this case, the backup copy that we still have in the cluster will be promoted and become primary. And a new backup copy will be created in background on somewhere else in the cluster on JVM 3 or 4. If JVM 1 fails, again, if JVM 2 fails, we just lose the backup, and again, in the background, we'll create a new backup copy on JVM 3 and 4. So whenever we lose one of the nodes, we don't actually lose any data, and system remains fully available and fully consistent. And we obviously can lose the node in case of network partitioning or any other failure like power outage, software failure, or what's not. But even if this happens to one of the nodes, system is still consistent and available. There is also replicated cache, which is pretty much the same as partitioned. The only difference is that it forces Ignite to create backups on all the nodes. So you will have as many copies of each entry as many nodes you have. For example, in the same example, we have 4 nodes, 1, 2, 3, and 4, and the JVM1 is still primary for entry A, but now we have backups on all other nodes. This is obviously much more available than partition cache because the system will be fully consistent and fully available as long as you have at least 1 node. You can lose 3 of them, but the system is still available. But there is another trade-off here between consistency and scalability, because partition cache is much more scalable. If you have a large data set, you can't fit it into a single memory node. And that's how replicated cache works. Replicated cache requires that you can fit the whole data set into a single node. This is usually not possible for large data sets, so you need to choose an appropriate, go with partition cache if you have a large data set, and choose an appropriate amount of backups so that it's still scalable, but also available. Now let's let's go through a particular example of how backups can be used, and that's actually a pretty typical situation. I've seen this many times working with the customers and our users. Now imagine you have a cluster of several nodes, 6 nodes, for example. And these nodes are each node is deployed on a separate server, and servers are actually deployed on different racks of servers. For example, nodes 1, 2, and 3 are on rack 1, 4, 5, and 6 on rack 2. And each rack has a switch. It's not only switch, it can be also like a power source or anything that is basically shared between all the nodes in this rack. And clients go through the switches to connect to actually connect to nodes and get the data and update the data. And we also have a cache, which spawns all the 6 nodes. And there will be some distribution of the partitions across these nodes. Like for simplicity, let's imagine we have only 6 partitions, 1, 2, 3, 4, 5, 6. And they have this simple distribution. Partition 1 is stored on node 1, partition 2 on node 2, and so on. And we also configure a backup for this cache, one backup. And it will the backup partitions will be distributed, for example, like that. By default, it will be completely default distribution. You cannot actually predict how Ignite will distribute primary and backup partitions. So this kind of distribution showed here is perfectly valid. This can happen. And if you notice, for example, partition 1 is available only within the rack, within the first rack of servers. What this means is basically that when we lose the first rack of nodes, for example, if the switch goes down, when the switch goes down here on the left part of the cluster, all the nodes that are in the rack 1 become completely unavailable to all the clients. And all the data that were stored on this node also become unavailable. And in this particular case, this basically means that we lose partitions 1 and 3, which makes data inconsistent. And since Ignite is fully consistent system, it can't give any responses back at this point. So the system becomes unavailable. So how do we solve it? How can we solve this in Ignite? Ignite has a pretty neat trick. It's called Affinity Backup Filter. It's basically a custom function that you can provide in configuration. And to solve this problem, we have to make two steps. The first step is we assign an attribute, a special attribute to each node, which will basically define on which rack the node is running. Like, for example, we have an attribute rack, which can have a value rack 1, rack 2, and so on and so forth. And we just provide it in the configuration when we start the node. So when we start the node, we tell on which rack this node is running. And this information is available across the whole cluster. So any node can ask other node which rack this node is running on. And then we have to implement the backup filter. So backup filter is basically just a function. It's Ignite P predicate. Ignite P predicate is a function of 2 arguments which returns Boolean, true or false. The first argument is, and this function will be called every time Ignite assigns a backup partition to a node. So when Ignite creates a distribution of partitions across nodes, it first assigns the primary node for a particular partition, and then it takes all other nodes, goes one by one, and checks if the node can be, if a node can be backup for this partition or not. And in our case, so the first parameter here will be the candidate node that we are. It is a candidate to become a backup, and the second parameter is the list of nodes that are already assigned. In our case, we have one backup, so this list will always have one element, which is actually a primary node that is already assigned. And then we take the attribute value from the candidate node. So that's the name of the rack where the candidate node is running. And then we do the same for the primary node. We get the first one from the list, which is the primary node, and we get the value of the attribute. And that's the name of the rack where the primary node is running. And we want to allow this candidate to be a backup only if it is not on the same rack where the primary node is. So we return true only if candidate rack and primary rack are different. If they're the same, we say no, we don't want this node to be a backup because it will end up on the same rack where the primary node is. This backup filter is also provided in configuration when you create the cache, and it will be applied for every redistribution that happens in the cluster. So as a result, we will get distribution like this, for example. The difference is that now we have all the data available on each rack. So like all 6 partitions are available on rack 1, and all 6 partitions are available on rack 2. So this is guaranteed if we have this kind of backup filter configured in the cache. And now if we turn off the switch on the left, we still have all the data on the rack 2. No partitions are lost, no data is lost, data is still fully consistent, and therefore it's still fully available. And that's a typical case of network partitioning, by the way. I was talking about in the CAP theorem slide. So network is partitioned, we basically lose half of the cluster, but system is still consistent and still available. All right, let's move on to the next topic, which is persistence. Persistence is a very important part of any in-memory system. It's usually required to provide full consistency. And Ignite provides 2 ways of persistence. So first of all, first option, which is shown on the right, is something that we also have for a long time. It's an integration with a third-party store. It's usually used within memory when you're working with the data grid, within memory data grid, with the key value store. And third-party store can be anything. It can be traditional RDBMS. It can be MongoDB, Cassandra, HDFS, and what's not. So basically, it's a pluggable component, and you can integrate with any kind of storage. And this kind of integration fully supports read-through and write-through semantics. So as long as you use key value APIs, you can't actually lose the data, because when you read the data, it will be loaded from the storage if it's not available in memory yet. And anytime you update the data in the cache, it will be also propagated to the storage as well, so that the storage is always consistent with the in-memory cache. But for more complex use cases, like in particular when you use SQL language to interact with the data, you have to warm up the memory before running any queries in case you are using third-party store. Because basically there is no read-through is possible only if you know key value, if a set of keys in advance to load from the cache store, which is obviously not possible in case of SQL queries, in case of arbitrary search condition. So you need to warm up the memory. Another disadvantage of this approach is that, especially in case of RDBMS, in case of single instance RDBMS, it's a single point of failure, which is actually very bad for availability, because that actually means that when you lose the database, if the database instance goes down for some reason, the whole system is unavailable. So you need to take care of availability on database level as well. So you not only have an additional storage, an additional system you want to integrate with, but you also need to take care of availability of this system, because availability of Ignite will depend on the availability of the RDBMS, of underlying database. And in addition, it's also a bottleneck for writes, because anytime you update the cache, you can update the cache on any node. The updates in the cache are actually distributed. They're scaled out across the cluster, but all these updates will go to the single RDBMS instance, and that is obviously a bottleneck. The second option, which is shown on the left, is Ignite Persistent Store. That's the native persistent store. It's also a new feature which was released in 2.1, and it's basically a kind of an additional disk tier. You can think of it as an additional disk tier where you can store your data. The data is actually stored in pages, and any page can be either in memory or on disk. Actually, disk has everything, but some of the pages can also be in memory. And it's completely transparent to the application. So whenever you read something, you execute SQL query or you use key value API, it doesn't actually matter in this case. Ignite will automatically fetch any pages that are not in memory yet. And therefore, you don't need to do any memory warm up like you had to do with a third-party store. Even if memory has no data at some point, you have everything on disk after cluster restart, for example. Then you can still execute any queries, you can do any updates, you can use any APIs. The data is still available and fully consistent. This brings multiple advantages. So first of all, as I already said, you don't need memory warm-up, which basically means that you can instantly restart a node or a whole cluster even. So if the cluster goes down for whatever reason, it becomes unavailable, but then you just restart the nodes, and that's all you need to do. You don't need to preload the data, which typically takes time, of course. You just start the nodes and the system is back. You can continue using your applications, system is available again, and it's still fully consistent. It's also fully distributed. Every node has its own part of the data on disk, so it's not a bottleneck, and there is no single point of failure. Okay, let's let's also deep dive into the persistent storage a bit. So first of all, as I already said, it's a distributed disk storage. So every node has its own part of the data. And this slide shows kind of the architecture of a single node. That's how it looks like on each node. You can have multiple caches. Each cache will have multiple partitions, and for each partition you will have a separate file. Obviously, each node will have a subset of partitions. Like here we have 1, 10, 564, for example. All other partitions will be on other nodes. Indices are also stored both in memory, can be stored both in memory and on disk. So if you lose the cluster, if you lose the in-memory data, you don't lose indices as well. And they're also stored in separate file. You will have a single file per cache to store the indexes. And there is also the write-ahead log. Write-ahead log is basically just the log of all the operations, all the updates that are happening on the cluster, and it can be used for recovery in case of failure, in case of disaster. All write-ahead log files are also archived. So basically, the actual main write-ahead log is used to store the latest updates, and there is also an archive folder that holds everything that happened in the past. Okay, so a little bit about how the persistent store actually achieves consistency. Just a little bit of architecture and about how it works under the hood. So there are two main things that allow a persistent store to be consistent. First of all, it's write-ahead log, as I already mentioned. So the write-ahead log is an append-only file. So anytime you persist something, you update something in memory, in RAM, this update is first persisted into write-ahead log. Write-ahead log is append-only file, so it's relatively fast. So just a log of updates. Because I mean, if you write the data, for example, the actual data somewhere in the data files, you will most likely write somewhere in the middle or do something like that, which will be much slower. So that's why we chose the write-ahead log here. It's an append-only file, which makes it much faster, and it can be used to recover the data at any moment of time. So if you have a failure, you have all updates registered, persisted there in the write-ahead log, so you can recover using the write-ahead log. And also there is a checkpointing mechanism, which is basically just a periodically triggered process, which takes all the data from RAM, all the data in RAM which is not persisted yet, and persists these data, these deltas in the partition files that we already seen on the previous slide. So this allows us to reduce the write-ahead log size, because if we just use the write-ahead log, it will become very, very big because we will have all updates there. We still want to have files that actually store the actual data, the actual keys and actual values. But the process of updating these files are much slower, so we do this in background. And once we do this, we can reduce the size of write-ahead log. So basically, these partition files created during checkpointing, they store the actual data. They replicate the data that is in memory, and the write-ahead log has like the latest updates since the latest checkpoint. So that's how Ignite persistence works on a high level. Now I will talk about data center replication. That's a completely separate feature. It's available in GridGain Enterprise Edition. So basically what it allows you to do is it allows to replicate data from one data center to another. So imagine imagine a situation when you lose the whole cluster, right? So all the nodes are going down due to global power outage in the data center, for example, or something like that. System obviously becomes unavailable if you have only this one cluster, because you don't have any nodes, you don't have any data. You need to restore the power in the data center, you need to restart the nodes. It will take some time. But you can actually have the second data center somewhere far away, maybe in different country, and you can replicate the data to that data center. So basically what happens is that active data center, which the applications are working with, listens to all updates in the cache or caches, batches these updates, and asynchronously sends them to another data center. So that basically this second data center always has the same data that data center one has. And if this disaster happens, if the active data center goes down, you can switch the applications quickly to the passive data center so that they continue working. The system stays available for them. When the active data center is back, you switch back, and actually you are at square one. So what I described here is actually active-passive mode, when you have an active cluster and a passive cluster. But you actually can have you can also use active-active mode, which basically means that both clusters are used by applications, and applications use both clusters to update the data, and they replicate both ways. So the data center one gets an update and replicates this update to data center 2, and data center 2 gets an update and replicates to data center 1. That's a bit more complicated use case because it requires conflict resolution, because obviously it's possible that both data center update the same entry in cache, and you need to somehow choose between these two values. We have several mechanisms provided out of the box for this kind of smart conflict resolution. But even if you need something much more specific, much more data specific and use case specific to do this conflict resolution, it's actually pluggable, and you can implement your own mechanisms pretty easily. Data center application, it actually supports up to 32 data centers. So these examples I provided are for 2 data centers, but you can have more. You can have up to 32 data centers, and you can have complex replication topologies, like data center replicates to data center 2, data center 2 replicates to data center 3, for example, something like that. We also have durable queues there, durable persistent queues. It's also kind of a separate feature which makes sure that the active data center does not run out of memory in case of passive data center goes down. So like imagine a situation when you do a replication from data center 1, which is active, to data center 2, which is passive, and then data center 2 goes down. First of all, you need to make sure that all the updates in the cache 1 are eventually replicated to data center 2. So it's not like you lose something, right? And when data center 2 is back, and in this case, data center 1 will actually accumulate all the updates in the persistent queue. It will be on disk, so that data center 1 does not run out of memory because of this, and it still accumulates all the updates. And when data center 2 is back up, data center 1 can flush all these queues into the passive data center to make it consistent with the data center 1. Okay. So, and the last but not least feature I would like to talk about is data snapshots. Data snapshots you can actually think of it as, it's similar to database backups, full database backups. I don't use the word backup here on purpose because the backup term has different meaning in Ignite. as I was talking before. So we call them data snapshots. Basically just a full backup of all the data that you have, full data set that you have in a cache or maybe all the caches. And here we support full snapshots, which is the snapshot of all the data. It's basically a file that has all the data, or set of files that has all the data that you had in the cluster when you created the snapshot. It's a full state of the cluster. And it obviously takes some time to create this, right? If you have a very large cluster with a lot of data, it will take some time to create the full snapshot. So you don't want to do this very frequently, right? So that's why we also have incremental snapshots. Incremental snapshots is a partial state. It's basically a delta since the latest full snapshot. So generally what you will do is you will create a full snapshot, maybe once a day or once in several days, for example, sometime overnight, usually. And then you will create incremental snapshots based on this latest full snapshot, and you will do this much more frequently, maybe once every hour or 2 hours, something like that. So this basically helps you to not waste a lot of time on creating these snapshots, because most of the time you will create only incremental snapshots, which are relatively small and take relatively less time than full snapshots. But still you can return to, if you do this every hour, for example, if you take an incremental snapshot every hour, you can return back in time not more than an hour, which is sometimes is pretty useful. And you can also create schedules. So basically you can, instead of doing all this manually that I just described, which will not be effective, of course. So you can create a schedule that will do this automatically for you. So you can create a schedule which basically will create the full snapshot every day and incremental snapshot every hour. This has actually different use cases. One of the main use case is an ability to restore the cluster state on different cluster, the data state on different clusters. So basically, imagine you have some problems in production, and you want to do some additional investigation. You obviously can't do this on actual production cluster. But what you can do is you can take the snapshot, take a snapshot from the production cluster, take the data from production, and deploy it somewhere else, maybe on a smaller cluster somewhere in development or in testing environment. And you can do any investigation there. You can corrupt the data, you can do whatever you want. You can do some load testing, maybe benchmarks on the real data. So this is pretty useful, right? And another very important use case for data snapshots is recovery from different operational errors or software errors. So basically, it's possible that your data is corrupted not due to network partitioning or node failures or something like that, but due to operational error or software bug, right? Like for example, there is a operator which basically removes all the data from the cluster. From Ignite's point of view, it's a perfectly valid operation. Ignite cannot detect this automatically and make the system unavailable in this case, because it's a valid operation from Ignite's point of view. So it's up to the application, up to the DevOps to detect this, to stop the cluster, and then recover. And to recover, they need to have recent snapshot of the consistent and not corrupted data. And also the data snapshots are fully managed. We have a special screen on the web console for this. And actually I want to do a quick demo and show this particular screen and how it can be used to create snapshots and to restore from snapshots. Okay, so I already have like a small cluster running on my laptop. Let me switch on the presentation mode first. So let me show you the configuration first. So as I said, I already have a small cluster running. And this is the configuration file I used to start this cluster. So I use this configuration file on every node in the cluster. And there are several important things that I want to go through that are actually pretty simple. So first of all, we need to enable persistence. That's an important part. Persistence is required to enable snapshots. So if you want to use data snapshots, you need to have persistence, Ignite persistence enabled. It doesn't work with in-memory only data. It doesn't work with third-party persistence. So snapshot is actually taken from the on-disk storage. So you need to have Ignite persistence enabled. And for this, we set up this persistent store configuration being here. We also need to actually enable snapshots. So to use snapshots, you need to explicitly enable it. And by the way, these objects, persistent store configuration and snapshot configuration, they contain a lot of different parameters to tweak the behavior of the persistent store and snapshots. Like you can configure the folders where you want to store frequency of checkpointing and persistent store, for example, and so on and so forth. So here we just use default settings for simplicity. And we also have a cache. This is an accounts cache. It will just have a bunch of accounts over there. Nothing specific here. We just give it a name, and I also provided the indexed types properties just to make sure that I can query these accounts using SQL just to visualize it on the web console. All right, so yeah. So this is just the code that I will run now. It starts a client node. It then activates the cluster. That's also one of the important additions that we have in 2.0 is basically cluster can be active or inactive. So you can inactivate cluster at any moment and activate it back. Inactive cluster is not able to provide any responses with the data or anything else. It basically just gives you an error whenever you try to do anything with that cluster. And if you're using persistent store, it's required that you explicitly activate it after you have all the nodes available. So like if you have a cluster of 4 nodes, for example, you first start all 4 nodes, and then you explicitly activate the cluster. Before you do this, cluster is actually unavailable. And then we just populate the cache with multiple accounts with random balances. We just use data streamer and create random balances and create new accounts. An account, by the way, is a very simple object. It's just account ID, name, and a balance. All fields are queryable, and I will use it in a second. Okay, so yeah, let's run the example first so that we have the populated cache on our cluster. So it just starts the client connects to the cluster, activates it, populates the cache, and then exits. So now we have a cluster with the data. There is a cache that has some data. Now let's go to the web console. Okay, so I'm going directly to the snapshot screen that allows you to manage the snapshots. And there are 2 main features. The first one allows you to create schedules, as I described before. So basically, you create a new schedule, like my schedule, for example, which will create snapshot. You can also delete snapshot or move snapshot for creating archives, for example. We'll create a schedule which will create snapshots. It will create a full snapshot every day. So we specify that it creates full snapshot daily, and we will also create incremental snapshot every hour. And here you can specify whether you want to create a snapshot for all the caches that you have on cluster, or maybe specify particular caches, like only accounts cache, for example. When I click set, it appears in this table, and now it will automatically do this job. So it will automatically create all the snapshots as specified in this configuration. You can also enable and disable the schedule in the runtime. And if you don't need this schedule anymore, you can just remove it from this screen as well. Okay, let's now you can also explicitly create the snapshot from here. Let's start with creating a full snapshot. So this one will just create a full snapshot for all caches that we have. We have only one cache, so it will be a snapshot with this one cache. So it creates the snapshot, and it appears in this table. So that's the full snapshot we just created. It has an ID. It's a full snapshot that was created right now, and it also shows that it was created by me. And now we can also create an incremental snapshot. It will be based on the latest full snapshot that we created just now. Okay, so now we can expand this, and we see that there is a full snapshot with one incremental snapshot. It shows it here, and that's the actual incremental snapshot. It's a separate snapshot. It has its own ID, but it's an incremental snapshot, and you cannot restore from the incremental snapshot without having the full snapshot it corresponds to, because that's just a delta from that full snapshot. So now let's go to queries tab here and query some data from our accounts cache. I'll just get 5 first rows in the table. So we see we have some accounts here with different balances. And now let's imagine that something bad, really bad happens. We basically will update all accounts with zeros. We will nullify the balances in all the accounts. That's actually a real story. I've heard this in one of the major banks I was working with. They had that actual situation. All the balances, maybe part of the balances, were basically nullified due to either software error, software bug, or some operational error. So let's do this. Let's just nullify all the balances. Now, if we query data again, we see zeros here, which is obviously bad. All the people lost their money. That's a very bad situation. We need to fix it somehow. And it's very easy to do if we have snapshots. Now we go back to the snapshots screen. We choose our incremental snapshot, which is the latest one. That's the latest state of the data. And we go to Actions menu and click Restore. So the data is restored. Now we go back to the Queries tab and we query data again. And we see that we have our balances back. So even in case of this very bad situation when we just do something stupid and corrupt the data, we can recover if we create these snapshots periodically and regularly. Okay, so that's actually it from my side. I'm ready to answer questions, and I will hand it over to Elisa now.
Okay, Valentin, thank you. All right, so let's go through some of these questions here, and there's quite a few of them, and bear with me. Okay, so the first question is about using third-party store. In the case that the third-party store or the database is not available for a few minutes due to failover, how is the data handled in memory that needs to be propagated to the database? Will we get exception on lost data? Will the data be queued somehow until the database is available again and then do a write-through or a read-through?
Yeah, so you actually have multiple options. So the question is what happens if the database is down, but you continue to update the in-memory data. So there are basically two main options here. So by default, write-through semantics are used, which basically means that anytime you update something in memory, it's synchronously propagated to the database. And since it's synchronously propagated, you can only fail in case database is unavailable. So in this case, you will just get an exception telling that the database update was not successful. There is also right behind option, in which case you don't wait synchronously for any update. for any database update. You just update in-memory cache and then put this update somewhere in the in-memory queue, which will be eventually flushed into the database. So this is, first of all, better from performance standpoint, from the update latency standpoint. It also makes it a bit more available, because even if you lose database, it's just accumulated in that queue. But at the same time, it's not fully consistent, because if you lose the node that holds this queue, you can lose some of the updates. So you can get the state where cache is not fully consistent with the database. So if you need full consistency, you will for sure use write-through mode, and in write-through mode, it will just fail with the exception, with an exception in case database is unavailable.
Okay, next question. How far apart do data centers need to be to use data center replication? Are two close-by data centers connected with multi-strand dark fiber considered two racks or two data centers?
Oh, it actually, yeah, you can. It can be different. So two racks. What I meant by two racks is basically I meant a single cluster. It's a single cluster. It's a single topology. And generally, it will be in a single data center somewhere in the local network. It can be multiple racks of servers, multiple switches, but it will still be a fast local network. Two data centers are two completely independent clusters. And that's the value of this feature, actually. It replicates the data between completely independent clusters, which are usually geographically distributed. They can be in different buildings, in different cities, maybe in different countries. You can have two clusters in the same data center as well. There is no limitation. They can be very close to each other. But generally, this feature is used when you have two separate clusters, which are relatively far from each other, which use global network, not the fast local network, which has less guarantees, obviously. And in this case, you will use data center replication.
Okay, next question. How does Ignite Store work with SQL for objects that are not in memory?
Yeah, so I didn't dive really deep into this, but basically the latest version of Ignite has the page memory architecture, which means that all the data is stored in pages, and any page can be both in memory and on disk. And disk has all the data, disk has all the pages, and it's kind of a superset. And memory has a subset of these pages. And it's completely transparent to any kind of operation. So when you access the data, you access a particular page. And Ignite will just detect if this page is in memory already or not. If it's not, then it will fetch lazily from disk into memory and provide the result. So as a matter of fact, memory is optional. So you will, of course, usually use it for performance reasons, but it's not even required. So with the latest version of Ignite, if you use this persistent store, you can have everything on disk and work with Ignite just as with distributed disk database. But generally, of course, you will have part of the data in memory to provide better performance.
Okay, next question. How does creating a snapshot impact performance of a GridGain system?
Well, it's pretty much background process. So it basically, first of all, it affects only, it can, even if it affects only on disk data. So it doesn't even touch the data that is in memory and that is usually like most performance sensitive. So generally, I don't think it will have a serious impact on performance because it is basically just copying the files, the data files into a separate folder pretty much. It's more complicated than that, but you can think of it as a simple process. And actually, these data pages are updated in background within the checkpointing process I was talking about on one of the slides. So which basically means that I would not expect any performance degradation because of snapshots. And that's the rare event. You usually do this like once every hour, or maybe even every once a day only, like overnight when you don't have high load on the system. So I would not expect any performance degradation because of using snapshots.
Okay. What happens if we do not specify backups for partitioned caches?
In this case, you will, so this actually means that as long as you lose one of the nodes, you lose some partitions from the grid. That's the main implication of that. So usually you will have like one or two backups at least to make sure that an occasional failure of one of the nodes doesn't bring you into unavailable state.
Okay. How does Ignite work with strongly bounded data, hibernate-like proxies?
I'm not sure what strongly bounded data, to be honest. But as for Hibernate, we have different types of integration with Hibernate. First of all, Ignite can be used as the level 2 cache for Hibernate. And you also, since Ignite can be used as a distributed SQL database, you can actually use Hibernate and just use the Ignite JDBC driver with Hibernate and connect to Ignite through Hibernate. So whatever you use in Hibernate, in your Hibernate data model will be basically translated to SQL queries, and Ignite will be treated by Hibernate as a distributed SQL database, as any other relational database.
Okay, next question. Are snapshots consistent? Do they lock all data when they execute or are initiated?
That's a great question. Yeah, I don't think there is any global lock. It's obviously a concurrent process that can happen concurrently with any data updates or whatever happens. And basically, whenever you start to create a snapshot and then you do an update, it can end up in snapshot or can end up out of the snapshot. But this basically means that if it doesn't end up in this snapshot, it will end up in the next snapshot because it will be created on the latest state of the data.
Okay, we have a time for a couple more questions. So the next one is, does it make sense to have a backup for replicated caches? With replication, each node already has all the data, so backup seems redundant.
Well, yeah, replicated cache is basically partition cache that has backups on all the nodes. So it will have as many backups as many nodes you have. So like if you have 6 nodes, you will have for every entry you will have one primary copy and 5 backups. And this is done automatically. So you just specify the cache mode. You tell that the cache is replicated, and Ignite will automatically create backups on all the nodes. Unlike with partition cache, where you explicitly specify the number of backups you want to have.
Okay, and then let's see here. If Ignite is configured with disk persistent store, he says 2.1.1 version, and cache is configured with 0 backups, will Ignite load lost data from disk pages onto new nodes?
The amount of data you have in memory depends on the configuration of memory regions and memory policies, which basically defines the maximum amount of memory that you can allocate. So obviously with the same, when you have redundancy, when you have backups, you can fit less unique data in the same amount of memory. But it doesn't break consistency and it doesn't break availability as well, because as long as you have all the data on disk, you can read the data from disk, and the data is available and fully consistent.
Okay, and our last question for the day is, in case of replicated caches, how many nodes must be updated before the ACK is issued?
You have to update all the nodes. There are also a couple of different modes that you can configure. There is a full synchronous mode, in which all the nodes are updated synchronously. So when a client issues an update, it goes to the primary node first, then primary updates all backups, and the client will wait for all the nodes to be updated. So when the client receives the response, it actually means that all nodes in the cluster are updated. And there is also primary synchronous mode, primary sync, in which client waits only for the primary node. And primary then will asynchronously update backup copies. But again, for full consistency, you need to update all the nodes synchronously.
Okay, and this brings us to the top of the hour. Valentin, thank you so much for an informative session. We had lots and lots of questions. There were a couple that were not addressed. I'll make sure that Valentin gets a copy of those questions. And Valentin, thank you so very much. And audience, we hope to see you on a future show. Thanks again,
Yep.
everyone.
Thanks everyone for listening.